Alright, so the first thing we have to do here, our first step, is some cross-section work. Let me redraw a picture of the cross-section over here. Let's say something like this. We've got this sort of T shape. And you notice I'm drawing this nice and big because I'm going to label on here a couple of important points. I'm not going to label all the dimensions on this. I'll label the ones we need as we go. In red, I'm going to label parts 1 and 2 of the cross-section, and I'm going to label the centroid locations of those respective pieces of the cross-section. So this dimension right here, that's 1 inch. This dimension right there is 4 inches, and of course they are oriented on this center line right here, just like that. Okay, so our first goal is to find the location of the centroid of the composite section, and that's going to be a function of the area and the centroid location of each section. So what we're going to do is we're going to write an equation that looks like this: y bar of our composite section, and I'm going to measure using the top down as my datum, as is suggested in the original picture. It's going to be the sum of the y tilde a over the sum of the a. You remember that from statics last year. So here we've got sum of the y tilde a. It's going to be 1 inch times the area of that top piece, which is 2 by 12, plus a total of, let's see here, it's going to be 6 inches times 8 times 2. I'll explain all these things in a minute. And then the area is 2 times 12 plus 8 times 2. All right. So this one right here, this one, is this one. And this 6 is this distance right here. That's 6 inches. That's the location of the centroid of piece number 2 with respect to our datum. And then the 2 times 12, this is the area of 1. The 8 times 2, that's the area of 2. Okay, you get the idea. Anyway, y bar turns out to be 3 inches from the top. So if I could do that in blue, that means somewhere, let's say right there, is our centroidal coordinate system. So this thing right here is 3 inches. Okay, so that was easy enough to do, and you can see that that's located on the center line. Next thing we have to do is calculate the moment of inertia. And let's start here. Let's start with IZ. So if we call this, for the moment, we'll call this Z and this Y, consistent with what's on the front page. I'm going to write this all out, and I'll label it in just a minute. We're going to do IZ, and here we're going to consider piece number 1 and piece number 2 separately. We're going to do a BH cubed over 12 plus parallel axis theorem part, as you'll see in a moment. So let me just write it, and then I'll label what the pieces are. All right, so it's 12 times 2 cubed over 12 plus 12 times 2 times, let's see here, 2 squared plus 2 times 8 cubed over 12 plus 2 times 8 times 3 squared. Okay, now let me label exactly what those things are. Let me say first that this is related to area number 1. That's related to area number 2. The BH cubed over 12 part in each case, I hope, is clear. Okay, that's this part right here and this part right here. And the dimensions are labeled on the figure on the previous slide, and the figure from the book, of course. Let's look at the areas and the AD squared part. Okay, so this is the area of piece number 1. This is the area of piece number 2. And then the D's are these distances right here. And let me put these in this nice bright green color. So the distances are the distances from the centroid of each piece to the composite section centroid. So this is 2 inches. And this distance right here, this happens to be 3 inches. Okay, so that's where that 2 comes from and that 3 comes from. The answer to this turns out to be 333.3 inches to the 4th. Okay, that's IZ. Now IY is going to be a little bit easier to calculate. There's just BH cubed over 12 kind of pieces because, as you saw up here, all of the centroids are located on this same center line. So by the argument of the parallel axis theorem, all the d's in the AD squared parts, all the d's go to 0 when we're looking at the y-axis. All right, so we can just go ahead and write where we're going to flip the b's and the h's from the IZ calculation. So it's going to be like 2 times 12 cubed over 12 plus 8 times 2 cubed over 12. That turns out to be 293.3 inches to the fourth. Okay, so you can see that what was B up here, let me just sort of mark that, what was B up here is now H here. What was H up here is now B here. So it's sort of like we turned the T on its side and looked at the B's and H's in that context. All right, nonetheless, what we found is IZ and IY. And now we have to think a little bit about whether we've defined our coordinate system correctly. So let's make an observation here. Let me do this in blue over here in this inset. What we found is that IY is less than IZ. Okay, and that means that Z is the principal axis of inertia corresponding to the maximum moment of inertia. Y is the minimum. And so this conforms to our needs with respect to how we define the coordinate system. And you can look at the book on page 323 for a description of this. Now, we talked about this in class a little bit. Basically, what this means is that we point the z-axis in the direction of maximum inertia. We point the y-axis in the direction of minimum inertia. So what that means is that the way we've defined the coordinates here with z and y are correct, and then that means we can get theta positive measured from positive z to positive y. So the way we've set up the problem is consistent with the way the book wants us to, so that we can derive the equations that are derived in the book are going to be useful to us. Okay, so that was an easy enough thing to do, and there was a small check we had to do there to make sure that we've got this all set up correctly. Let's move on to the next step, which is number 2, some moment work. Okay, now this is pretty easy to do. We can go ahead and write mz is going to be equal to m times the cosine of theta, and that's equal to 150 times the cosine of 120 degrees. That just turns out to be minus 75 kip inches. My is equal to m times the sine of theta. That's 150 kip inches times sine of 120 degrees. This turns out to be 129.9 kip inches. Okay, so I do want to point out here the signs, SIGN signs, which are negative for mz and positive for my, because when we go to step 3, which is to look at the stresses, we're going to use an equation that looks like this. We're going to use stress is equal to minus mz times y over iz plus my times z over iy. Now, let me, I don't know how to denote this. If you're sort of going through this quickly, let me just put a big, huge, great big star and go over it a couple times next to this equation. This is actually a really important equation, and the reason it's important is because obviously it gives stress, but we have to think about the signs of everything. We need to think of the signs that are present in the equation. We need to think of the signs of the moments, and we need to think of the signs of the geometric coordinates y and z.